Sorry for the delay. Any questions for any previous content? Okay, Professor? Yes.
Sometimes you wrote the transformation as U operator, U dagger.
Yes.
And sometimes U dagger O U.
Yes.
Well, when we consider the arbitrary transformation for the vector or tensor, then can we argue that those kinds of transformation both?
So you're asking, turn on the slide. So
I want to know the
Yes.
goal of two kinds of transformation.
So you're asking, just make sure, you're asking when I write, the question was, when I write given an operator O, like, which one am I supposed to write? Is this your question?
Yes.
Good. So the convention is, if I view this as a Heisenberg picture, right? And then if the convention is I take the state and transform like this, then if I demand the same symmetry transformation, either Schrödinger picture in terms of a state or operator in Heisenberg picture, then this will transform in the language of state for now. It will do this, right? But then I can match this to a Heisenberg picture, considering state being stationary. Then I will say that O is transformed as this. Right? Okay. I thought in the discussion of constructing scalar field and so on, we've been using this convention. Having said that, you still have a question? If so, what is your question again?
Okay, then for the two expressions U theta U dagger in homework or in quantary algebra, and you wrote there that expression, and I think this is a compatible result, but is there any physical interpretation of that result, that expression?
Okay. Probably it's a matter of convention. Once you pick a convention, you have to be consistent throughout, right? It is possible that maybe during the lecture versus my homework, maybe convention has not been completely consistent, but I'll say this will be my convention. Everything else should and can be done in a consistent way. Okay. Any other question? Okay. So if not, let's jump in. So far we talked about, first of all, how to construct a consistent causal scalar field. And then last time we talked about, can we now take a field operator as a fundamental object, and then how those 5 conditions we imposed pops out, right? And then we said that, so this is a very quick recap of what we talked about. So then we say that the first condition, which was about the causality, right? And then the fifth condition previously, which was linearity, this being linear in these two equation operator, that was replaced by saying that, I want to demand that the quantum field has to satisfy this, because that's how we get the correct relativistic equation. And the fact that this equation is linear in field guarantee that it describes a free propagation. It is consistent with the fact that these are linear. Causality not imposed as a initial conditions, right? Causal initial conditions, and then we say, we are going to impose equal time commutation relations. And then we also derive, if we impose this, and then if we derive this, we get this. Either plus minus sign, I don't remember exactly, but at least it was this consistent two boundary conditions. Okay, impose. And then, basically 3 of The second was hermeticity, which is optional. And 3, 4 was basically imposing Poisson. Right? So we say that therefore we can change the grammar saying that I want to have a field theory which spits out this equation, Klein-Gordon equation, as a governing tree-level or free-level equation to be solved with this commutation relation. Then we want to do a relativistically invariant field theory, so we are going to impose this. Hermeticity once again is an option. So today we will start our discussion, therefore, that we will now start talking about yet another layer of construction that spits out all these result conditions that we wanted to have for scalar field as the outcome of a formalism. Okay, so that's the discussion. We're going to start talking about classical field theory, and then we're going to perform canonical quantization. We'll see that all these conditions come out as an outcome. Okay? So here, roughly the picture is that suppose we had a classical mechanics. Okay? So this is a classical description of a particle-like system, right? And then we can quantize it. We can quantize it to get a quantum description of particle system, so it's a quantum mechanics. Okay? Now, the sort of logical path we're going to take is that we're going to now consider a classical level infinite number of different freedom systems. Okay? As you will see exactly what sense of infinity, but like infinite number of system, and then we will start talking about classical field theory. And we will impose relativity. Then you can think about how to go to eventually quantized version of that to get a quantum field theory. So the path we're going to take is that, so I will briefly review how to deal with the classical mechanics, right? Okay? And then I will introduce classical field theory, and then I just do a quantization in terms of canonical quantization to get quantum field theory. Okay, so that will be the path, and by the end of this discussion, we will see that all these conditions will come out as an outcome rather than the new. So let's quickly review how we deal with a classical system. So let's review. So first part is quick review. How we deal with the classical mechanics. And then we're going to adopt the formalism to deal with a system of a field. Okay? So, how would you do that? Well, let's consider first generalized coordinates. Okay, so for instance, you can imagine that you have n, say, particles. You will have a x vector for particle number 1, which will include x. Who can rescue me? Okay. I'm in trouble. So that was not the best choice. Q, let's do it. So coordinate Q for the first particle, which will be like x1, y1, and z, right? And then you can have n number of them. And I can smoosh them. I can smoosh them together and just introduce the QA. Okay? Where in this particular example, this thing has to run from 1 to, for instance, 3n. that's the generalized coordinate. And then suppose we take an action description. So we can introduce the action where I integrate the Lagrangian, which is a function of a generalized coordinate and its derivative. And then I can integrate from something like t1 to t, right? And this combination, so here we are taking q and q dot as our control variables, meaning we can change the position or velocity and see what happened to the system or measure that. So this is this variable is called the configuration space, right? So then we can ask, how dynamics is determined. And what is the dynamical equations of motion? And what you do? Now you use a least action principle. So equations of motion, and whenever you say that equation of motion can be derived by Hamilton's principle. There's many names for this, right? There's a least action principle, and there's a variation of principle. All the same thing. So you basically demand that you consider now varying this variable to an arbitrary variation. You also consider variation of velocity with some arbitrary variation, right? So under that, you check how action changes. So that can be computed because you know how Lagrangian in this case is a function of these two variables. So you go through hopefully formula exercise. Okay, so far so good. Now this is equal to d dt delta 2a. Okay? Because that's the difference of two delta q's. That means that this is difference of this thing, so that means that q dot plus thank you minus q dot, right? So that's this notation. So if you subtract, you can put the dt. You know what I'm saying? d dt q delta q minus the other, and you should get this, right? You rewrite it as that. Anyway, so now what you can do the integration by part, but we are going to be a little bit careful when we do that. So this can be written as a total derivative of delta qa minus yes, d dt delta. Okay, okay, so you can plug this in. Then if you do it, you get the following answer. So let me just put here that is more cleanly. So I'm going a bit fast here because hopefully you've seen this at least once or hopefully many times. So delta S, therefore, is given by T1 to T2 dt with that term. That's one. And then that's not all, because you have this surface term, meaning there's a dt integral, but there's a total derivative. You can cancel dt, so that appears as a total surface term. And that surface term should be plus Okay? So far, this is straightforward calculation. Now, what do? Well, we say that we want to have a minimal action under arbitrary variations. Right? So if you demand that, naively, it should be 0. Now, here we can go as follows. So the simplest case is that I want to demand that the variation of the generalized coordinate at either t equal to 1 or t equal to 2, meaning at the boundary of the 2-time integral, I want it to be vanishing. That's one option. But that's not the only thing you can do. Basically, you want to ensure that this term goes away. Okay, so therefore, in general, this surface term basically determines a boundary condition that you want to impose on your physical system. Okay? And one, again, way to go about it is to impose this Dirichlet boundary condition. Let's say that the variation is 0 at the boundary. Then, in the work, any point in the work, because you're considering arbitrary variation, you get a equations of motion. So that's you basically equations of motion. Let me color chalk. So if you do that, you get this is equal to 0, and obviously that has a name, or red is not proper. Let me do this. It's called Euler-Lagrange. Okay, so that you have seen at least once before. Now, what are we trying to do? I want to quickly review, given this classical system, how do we quantize to get a quantum version of the description, right? That's the path we want to discuss. And then we will do the same thing for classical field. So, we want to quantize the system to do classical mechanics to quantum mechanics. Not need to, but need to go to Hamiltonian picture. So here, by need to, I mean if you want to do what is known as a canonical quantization. So there is a way to quantize the system just using action or Lagrangian. Okay, probably you have seen it, but that way of doing it is called the path integral. Okay, so we will discuss that at some point. Presumably not this semester, but in the second part of QFG. Okay? But here, let us first focus on one way to quantize the system known as canonical quantization. So to do that, we want to pass from a Lagrangian to Hamiltonian picture. Okay? So let's do it. Because that's the one that give you slice by slice time evolution. Okay? Hamiltonian is what's performing the time evolution. You want to impose a causal boundary conditions that evolve, right? That's how we develop. So how do we get the Hamiltonian? We first look at the conjugate momentum. So let me say P sub A, which is dl dt2 dot A, right? So that's the conjugate momentum. Now, so this equation should tell you something. Just because you have seen this equation so many times, sometimes you can forget about the meaning of that. So this has a particular meaning. This tells you that Q dot is a variable of the Lagrangian and PA are conjugate to each other. Just like there's an X, there's a momentum, they're conjugate to each other. So this is showing you that they are conjugate to each other. Okay? Meaning they don't want to, they cannot appear in a single description. They don't appear simultaneously as a control variable. If you have a description where you control Q dot, this pops out as a function. Okay, so since Lagrangian is a function of Q and Q dot, here momentum is a function of Q and Q dot. So this is a function controlled by these input control variables. You cannot control simultaneously, okay? Or vice versa. The idea of now constructing Hamiltonian, as you probably have seen, Lagrange transformation is we do this, right? So you also have seen this. But let me spend some time to explain what exactly this equation means. Okay? You're taught to do this, but why? Okay? So let me just spend a few minutes to explain that. Some research group knows how to buy a good eraser. Definitely. Anyway. So what's the meaning of this? The name you know. This is Lagrange transformation. Well, what does it actually do for you? So this now is a function of a p and, let me put q first. Q and pa. You see, you want to control a dynamical function, meaning a function that encodes the dynamics in it. Now, instead of a q dot, you want to get a qp as your control variable, right? That's what it is. So you might say, oh, I don't know, I do see q dot. So that means that this means the following. So p is there. Now you view q dot as actually a function of q and then p. Okay? What it means is that when you have this equation, so possibly with the multiple variables, you assume that this equation can be inverted in terms of q dot. Right? Suppose you have n different kind of variable. For each of them, you derive a conjugate momentum. And you hope that as a matrix can be inverted in terms of q dot, right? If that inversion is successful, meaning the dynamical system you're dealing with is not a constrained system, okay? There's no funny like this variable is simply the same as that. Or somehow if you look at the equation of motion, conjugate momentum, you found that that's identically zero. Things like this doesn't happen. That's what I mean, okay? Then this equation can be inverted, that's what this means. And then there's an L, now there's a Q, there's a Q dot. Once again, Q dot is to be viewed as a function of Q and P. So that's how you get this complete inversion. However, let's understand one more step about this Lagrange transformation. Okay? In case you haven't sort of thought about that. So why this is supposed to invert the relation between these two, right? That's sort of thing you want to understand. Okay? Why that is a correct operation that guarantee you to invert that. So there's a many way of going about it. This is a classical mechanical system, but you probably have seen the similar thing in thermodynamics, right? So here first, a quick example. So in the context of thermodynamics, probably you have seen, so first of all, you have a energy as a function of entropy, V, N. So volume, and then the number of particles, right? So here, also probably you have seen that PdS minus PdV was mu dN. Again, in this description, in this representation of the physics, these are control variables. And then you see precisely conjugate object to entropy, conjugate object to volume, conjugate object to number. Right? Because this is precisely du over ds. Obviously, you have to control the N, and that's temperature, right? So you see, therefore, control variable and the determinant. And you may hope to switch the role of these two. Here too, exactly the same. So first, if you decide to switch the role of S and T, now you want to have a description where temperature is your control variable and entropy is a determinant quantity. Then, you get the Helmholtz free energy, right? So that thing, in this description, is defined as that. Probably if you look at it, this is the literal limits, but there's an overall minus sign, right? So in this description, if you now look at F, you get, in fact, So now T is your control variable, entropy is alpha as a function of a T, V, N, right? By the way, this as a function, P is not the same function as that, even though it has the same name. Okay, because now, for instance, this pressure should be a function of a TVN rather than SVN. So it's a different function. How do we get that? Well, anyway, so now if you can invert this relationship, that's how you get it. For instance, if you now want to change the role of a V and P instead, right? Guess what? In this case, you get what's known as the enthalpy, not the Hamiltonian, by the way. So this is U, P. And you will see exactly the same thing, but this is split. Okay, with over minus sign. I'm sorry? Plus P. Oh, okay. Because there's a minus sign. Good catch. Okay? Somebody remembers. Who had a interesting example? Anyway, so then suppose you want to also invert ST as well, right? You can try to do that. Then what do you get? You get free energy. Right? So you keep doing this transformation and you can keep going further. What if I want to exchange the mu and the n? What do you get in this case? In this case, you get quantum mechanical or grand canonical output. Yes, minus. Anyway, so this happens in physics a lot of times, right? So you want to have a control variable, and then there's a conjugate object, and when you want to exchange the role of the two, you go through this Lagrange transformation. Now let's actually explicitly see why this is the right thing to do. Okay, so let's just take that example of this Hamiltonian because we are working on it and check exactly why this is a good thing to do. So to do that, let's actually look at a variation of Hamiltonian. Okay, so I'm literally varying it. So what do I get? First of all, I get P. I can drop the little indices, but anyway. And then, now second time, I'm going to vary instead Q. So P. That's first. And then I'm going to vary Lagrangian. But Lagrangian, at least explicitly, it is a function of Q and Q dot. So I'm just going to look at, again, variation. First, we can vary with respect to Q. And the second time, we can vary with respect to Q dot. In case, that's a problem in case you have a complaint, why I'm not actually doing proper chain rules, because I told you that Q dot is to be viewed as a function of Q and P, but I'm not doing it. Okay, but I'm not violating anything, so you cannot sue me. Because I'm just looking at the variation, and then you can expand the variation, right, in terms of a partial derivative and proper rule, right? So which I'm not actually doing. Now, we remember that this is nothing but P. So the last term cancels exactly the first term, so we get the following answer. So Q dot A, delta PA. Right? So now, if the set of variables that we choose, QA, PA, are both independent and complete, by which I mean it's not like some of the P's are secretly related or some of the Q's are secretly related and so on. I'm not assuming that, right? There are a complete set of variables which are independent. Then, from this, you can see that in this Hamiltonian formalism, P, you get plus Q dot A, as promised, right? So you wanted to have a dynamical U description for which the relationship between the P and Q dot are exchanged. Okay? So you compare this. In the Lagrange description, this is control, this is conjugate. In Hamiltonian, this is control, this is conjugate. Let's finish it. So QA, what do you get in this case? Well, if you think about it, what this is. So what is this? What is that? What is that? Yeah, I just erased it here, right? So by equations of motion or Euler-Lagrange equation. Oh, I'm not supposed to call it yet. Okay. Is equal to dt, that, which is p. So it's p dot. So minus p a dot. Okay. So that's Hamilton's equation. So that you have seen it mostly, right? How to go from the Lagrangian to the Hamiltonian, and that particular combination, if you now think about it, work out several times, guarantee you to switch this. And now you see why, if you take original function, but this product of two conjugate variables, has the power of exchanging the role. Okay, with the proper minus sign. You might say, why for the Hamiltonian, we had a PQ dot first minus the original function. But in thermodynamics, we flip everything, right? There's an overall minus sign. That depends on your proposal. As you will see, it is this combination that give you positive, semi-definite, or function which is bounded from below. Okay? So obviously, if you flip the overall minus sign, you get some function which is now bounded from above. And thermodynamics, you want to run down somewhere, minimize something. Here we want to have a function eventually which is bounded from below. That's why there's an overall minus sign. Okay, so how do we quantize it? To quantize it in this Hamiltonian picture or canonical quantization, we introduce one more machinery known as Poisson bracket. Okay, so Poisson bracket, so consider now I have a two function. By the way, now in Hamiltonian formulation, these are my two control variables, right? And so they are known as, so this space spanned by these two are known as now phase space. Okay, versus configuration space in the case of Lagrange. So now let's consider two functions defined on this phase space. So I consider a two function defined on this phase space. So I'm dropping the label little a, just to save some time. So then, Poisson bracket of these two functions are defined as, so first I take this, take a derivative with respect to q, and then I do with respect to p. And then I do the same thing, but I change the derivative over. Okay, so that's Poisson bracket. This will give you some sense of algebra, or some algebraic structure. So the first property you notice from this thing is that Poisson bracket is antisymmetric. Obviously, if you change the rho, you get the because of the rho minus sign, because of this difference between the two. The second useful thing to check is this. So let's actually look at let's take a function. For this one, let's pick a function defined in the phase space. So there's a q, which can possibly have a time dependence with it. And then p, momentum, can have a time dependence with it. But in principle, this function can have its own explicit time dependence. Okay? There are time dependence through its dependence with the q and p. But in principle, it can have its own explicit time dependence. So now I want to check, I want to look at this. So take a Hamiltonian, I want to look at the Poisson bracket with the arbitrary function, okay, defined on the phase space. So what do I get? Well, let's do it. So q, let me put dot just to indicate that this is actually summed over variables. P, P, Q, right? So for completely standard. So let's do one more. So by Hamilton's equation, which we just worked out. By the way, I guess art of physics is like which side? It's always confusing and you never figured it out. But obviously, hopefully, this makes sense to you in the sense that if I take a simple Hamiltonian, like a non-relativistic Hamiltonian, plus v, some potential, if you take the derivative with respect to p, you get p over m, that is velocity. Oh, good. And if you take a derivative with respect to q, you get a dv over dq. That is known as a minus force. And by Newton's law, this is the force. So hopefully they can quickly get you to remember the sign. Anyway, coming back here, so we just talked about that. So that should give me q dot, and that should give me minus p dot, right? Minus force. So I'm about to write an important equation. Oh, my very good, nice. So what we learned from that exercise is a Poisson bracket between Hamiltonian and arbitrary space function, possibly with explicit time dependence. So up to minus sign. So if you subtract, what are you computing? Partial f with respect to p and dp over dt. Plus, again, I'm splitting up over minus sign. Partial f with respect to q and then dq over dt. So you're literally computing how f changes over time, but only through dependence of q and p, right? But in principle, you can have an explicit time dependence. So that object is like computing what is the total time evolution of modulo it might have its own explicit time dependence. Right? So if you literally compute the total time derivative, that's exactly what you do, right? You take the partial derivative, then q dot, partial derivative p dot, partial f, partial t. Okay, so that encapsulates everything except the last one. So that's that. So therefore, let's just remember one thing. Given a phase space function, the time evolution of that function in this classical mechanical system can be computed by in terms of Poisson bracket with the Hamiltonian up to minus sign plus explicit time dependence. Okay. So that's how we do classical mechanics. Now we can talk about quantization and equation at this point. Before I do quantization, now let me actually use this equation quickly. So let's take an example number 1. So now let's take f to be my q function. So what do I get? Then total time derivative of that thing. So remember, this is just q. Don't read this t as, oh, it has explicit time dependence. You know what I'm saying? So we'll take, say, qp and then explicit time dependence. Okay? It's just a q, right? That q. So that is Hamiltonian with qa. But again, don't write down this extra, right? Okay? So what is this? Let's actually, instead of remembering the Hamilton's equation, let me just go no-brainer, right? No-brainer, I'm just going to compute this bracket according to the definition. So since I have a q, I have to look at the term with the q derivative hitting the q, and the p derivative hitting the Hamiltonian, right? That's what you have to do. So you will get, I have to look at the second term, therefore. Are you with me? Okay? And then you say, aha, that's very beautiful. That's one of the Hamilton's equations. So in that sense, you see that this, formal machinery, known as a Poisson bracket, automate that. Okay, so let's do the exercise with now. What about if I take this PA? So if I do that, HPA. So now I want to look at the piece where partial derivative with respect to P hit this thing, the Q hit that thing. So that's the first term. So that's. And then you say, aha, that was one of another Hamiltonian. Okay? Yes.
Is there any reason for PA as a covariant and QA as contravariant?
Yeah, there is a reason. So P is defined as L over Q dot. So if I define the Q variable with an upper index, and this has a lower index. Okay, just like if I look at the derivative with respect to x mu, we write it as a del downstairs. The same thing. Okay. Any other question? Good. Now we are ready to quantize eventually. So let's quantize. So quantization in this Hamiltonian picture, the given QA of t, PA of t, first ingredient, you promote that to operators. Okay, that's first step. What about this algebraic structure? How should it be carried over to quantum mechanics? And so that is demanded by saying that if you have this thing, you promote to an operator statement, which is equal to IH bar with the Poisson gradient. So what that means is, for instance, we could have done another exercise. Let me just write the answer here, which is quick. So now if you look at a Poisson bracket with the Q and P, which should be obvious, so let me look at actually A with B. So definition of a Poisson bracket, can you see? Is this part? The derivative of Q should hit this guy, P should hit that guy. But opposite would give you zero answer, right? So you just read off the first thing, and then you can take the derivative with respect to QC, PC. So you get the delta AC, delta PC. You combine, guess what? You should get delta AB, right? That's our algebraic structure to be satisfied. So this is the rules for the canonical quantization. So for instance, QA operator, PB operator will satisfy A. Operator. Okay? And what else? So we can actually look at, for instance, the F operator over dt, which is made out of the Q and P right now, right? Will be now minus. Boom. Okay. H Hamiltonian acting with that, and then you can have its own explicit time difference. So this will be what is known as that. Whenever you get a new version, there's different names. Was that Heisenberg equations of motion? Okay. So what was a Hamilton's equation turns into Heisenberg? Now, there's one subtlety which we are not going to spend so much time, but we will certainly discuss it. Is what is known as operator ordering. So as you pass classical system to quantum system through this grammar or this scheme, quantize it, there's what is known as operator ordering ambiguity. So quickly, for instance, you had a classically, for instance, you had a QA, PA. It's a nice object, right? That's nicer function that you can have defined on the phase space. So as you pass on to a quantum, what did you do? What should we do? Should we do QP, or should we do PQ, or should we do QP plus p q divided by 2 or something else. And this question is right there because quantum mechanically QA is not equal to PA because precisely that the difference between the two is a quantum mechanical effect. So classical limit in this case, not just this case in general. So classical limit is defined by taking h bar goes to 0 limit. So what is a classical limit? There's no such thing as a classical, description, quantum description, which we are sort of taking the attitude for. However, I think it's fair to say that everything is a quantum mechanical system. Okay, everything is a quantum mechanical system, and in principle, every system, every physics should admit a consistent quantum description. And then what you see, which appear to be somewhat classical, like me waving my hand and chalk working or something, looks like completely classical. It's just because some of the system is macroscopically large enough, and for some reason, they can be well approximated by this limit. But it's not that it's intrinsically classical. No such thing exists. Okay? So everything is quantum, and then you just take a classical limit. And some system, is well described by such a limit. Some system is widely cannot be described by such a limit. Anyway, so just because this QP, the conjugate variables, don't commute fully in quantum world, that's why you have this ambiguity. Now, then which ordering should we take? That sounds like unclear question, right? Looks like given a one classical, looks like they can be separate. Well, one thing that you notice is that whichever thing you take, for instance, out of this thing option that I wrote, okay, it will all take to the classical limit to the same function, right? So at least it reduces the same thing. But you might worry about what about the other way around? Like which quantum description is the right thing to do? So just super briefly, it's confusing business. Okay, it's confusing business, and if you heard about or learned about what is known as a renormalization, there's a renormalization scheme too. So the statement is that you have to specify your ordering scheme when you quantize your system. You have to remember that, and then there's a measurement. You have to tell the experimental data that I quantize my system, therefore my quantum description is in terms of specific ordering. If somebody else took a different ordering scheme, and then when you try to compare to each other, you have to obviously cross-check, right? According to your scheme, you got this computation done in quantum theory, that's your prediction, there's a data, when you compare, you have to keep in mind. Same thing. So ultimately, next semester, when we spend a lot of time about the renormalization, there's a renormalization scheme, there's a regularization scheme. And none of the physics has to do anything with that. That's human beings' limit, and then we have to pick a specific description scheme. Okay? So when we compare to the data measurement to fit our parameters in terms of data, we have to factor in which scheme we use here too. For instance, in this lecture, we will see several examples of that. So we will see soon examples of operant ordering, such as I will discuss normal ordering and time ordering, and there's even what is known as anti-normal ordering. And something like a point splitting. In the context of a composite operator, there are things. Different ordering scheme is used for a different kind of aspect. So you choose different ordering to manifest a certain feature, which may obscure other features, but you just have to choose one, okay, depending on one. So, 54, no way. So next time we will, for the first time, talk about the normal ordering. And then when we talk about developing a perturbation theory, we will talk about time ordering. So this is good ordering for instance, if you want to look at the correlation functions of vacuum expectation value. This is good, in terms of killing some 30 terms that you don't want to see, for instance. Okay? And there are other proposals, that you can pick different order. Okay, so that's classical mechanics. Classical mechanics. Is there a classical mechanics class this semester? Do you have a classical mechanics class in graduate level? Do you? Okay, I could have replaced one of the lecture. Okay, so that's really okay. So that's the classical mechanics. Hopefully everything is familiar to you. Let's move on. Let's do quantum physics. Yes.
Such ordering does not appear when the potential is not a function of velocity.
Potential is not a function of velocity. It can be. Oh, you're asking like when this would ever pop up.
Yeah.
So yes, that's probably why. So yes, if as we talked about, if a potential is like some polynomial of the field itself rather than having a derivative in it, then as you can imagine, there's an ordering issue. But then you don't have to be super careful about that.
So we do not care in this course, but it is very important.
Well, like I said, you will see that even that, for instance, Hamiltonian, okay, as a pi square, that's pi, but then it will have a square. Oh, so that is problematic. Principally, you can view, and then there's a potential term. So already we will see that because of this, there's a notion of ordering issue.
Why?
As we will see. I hope I can get there, but because of this term, you will get not just, we will discuss, but instead of this, you will get both, and then depending on the ordering, there's issue. Okay? So we will have So therefore, when you have this derivative of a field, okay, at least you have to worry about it. Because by equations of motion, you can imagine that spatial derivative by equations of motion is related to time derivative. And time derivative is momentum. And so if you pick one of the things to be field itself, the other derivative used for the pi, it's sort of a combination of pi's and phi product.
It seems like that particular ordering can affect the equation of motion, right?
Which this one?
The particular ordering, up to particular ordering, some polynomials appears in the equation of motion.
Let me see.
So, for example, if there is q cubic and p term, then up to certain ordering there is q.
Then you already have to worry about operator ordering, right? If you have such a term in your Hamiltonian.
Yeah.
Yeah.
Then is there
Finish your question.
then does the haven't physicist doesn't solve this problem yet?
No. So for instance, this thing object, taking as a bit the average. For instance, this is called the Weil ordering. So definitely people thought about it, right? What is good, what is bad? But it's not like one is good for everything, the other is absolutely illegal. It's not like that. Because they reduce the same classical picture, and this is ambiguity. Okay, a certain all choice of ordering is useful for a certain feature, but they can again obscure some other features. So it depends on which object you actually want to compute. And for that particular computation, which ordering might be simplifying the computation conceptually and also technically.
그러면 만약에 expectation 이론에서 계산한 값과 실험에서 계산한 값이 다르면 오더링 다르게 해버리면 맞다고 하는.
No, that's what I'm saying. That physicists one took ordering A, physicists two took ordering B. They will compute their own thing, but in an internally consistent way. And then when they compare to that, that comparison will fix their parameter according to the choice of ordering. But when you try to compare two theories computation, you have to, now factor in which order you did, and therefore, let's see whether we have a matching or not.
이해를 그러니까 ambiguity라는 게 아직 해결이 안 됐다면
No, it's not that it's not some problem that has been solved. It's just that when you quantize a classical system, there's no unique choice of ordering one can pick. It's just multiple ordering possible. That's the sense it's ambiguous.
근데 그게 이제 물리적 값을 바꿔버리잖아요. 그러면
No, it doesn't change the physical quantity. It changes the relationship between data, actual measurement, and then theoretical expression that one computes. It is that relationship that changes. So there's data. Data is a single one, right? It's nature.
Yeah.
Suppose you pick your ordering, I pick my ordering. I compute my computation, you compute your computation, then you think you actually compute this thing. And then you have to match, right? You have to match. But then when you do the match, basically what the matching does for you is to determine parameters of the description, like mass or coupling constant. I will do the same matching, but according to my ordering, they will also fix my coupling constant, the mass, and so on. Right? Now time to talk about two theories. Right? What did you get? What do I get? Oh, why your coupling constant is different than yours? That's because of ordering ambiguity. We have to sort it out, which ordering you use, which ordering you use. Therefore we actually agree.
when we're saying that our prediction doesn't
Yeah, it's just a different description.
should be same.
Yeah, it should be the same. So therefore, when LHC measures a lot of data, I'll get to you, okay? When LHC measures a lot of data, different groups, like doing super careful, complicated, computations, especially when do a lot of loop computations, as we learned next semester, different group may use different renormalization scheme, different regularization scheme. So when they actually take the LHS data, fit into their thing, determine, I got this parameter, this number. I got this parameter, this number. Again, there's a ambiguity in terms of which scheme you have to pick to do the renormalization. In this case, it's quantization, but there's a renormalization. When these two groups have to communicate, they have to reveal, I use this regularization, like DMREG with the minimal subtraction. I use the Pauli-Villars with that description. And then they have to sort it out together. So this is one kind of that. Yes?
I think the observable doesn't change, but the parameter changes.
Yeah, it's a relation of observable to theoretical parameter. That changes. Yes?
클래시컬에서 QM으로 가는 극한에서 하바를 0에서 늘리는 그런 변화에서 스피는 저 과정에서 종속적으로 같이 또 나오는 결과인가요? 아니면 독립적으로 또 다른 것도 설명이 있어요?
So the question, if I understood, so if you try to do a reverse process of this thing, whether spin popped out as automatically or not, my answer is the spin is there already at the level of a Poincare representation. So what I'm saying is that, say you are given Poincare algebra. Say you want to do a physics, first classical and eventually quantum. Suppose you first want to understand the classical picture of a Poincare algebra, and you want to study irreducible representations of that, which we partly did. Now, that already knows that your object, called the particle, had to be labeled with the mass spin.
그러면 저는 포인카레 알제브라를 하바를 0으로 그린 클래시컬 극한에서 몇 과정을 취하면 당연히 그 스핀이 들어가겠다는.
You don't have to take any limit. Already fully classical limit knows about the spin already. One of the labeling has to be spin. So okay, so let me just write one thing. Okay, so take a Poincare algebra, and there are two. So you can compute. Don't worry about it. Doesn't make sense to you if it doesn't. There's another way of studying the Poincare, the representation theory, and you can look at the quadratic Casimir, which we didn't take that course. Okay, and then if you do it, one of the quadratic Casimir, so which is basically a set of operators or object that commute with the rest of it. Because you look at the, so that one is the t squared, which is the mass, and the other, if you use probably is the spin square. Okay, so okay, maybe I wasn't completely correct in that, you know, probably we're still talking about commutator. That means probably I'm talking about still operator in this sense. Yes. So in that sense, this thing already knows about it. You can say, you know, what is this limit in that case? But I don't think this algebra is related by IH bar limit.
J는 H가
What do you mean? I, J, epsilon J, you think there's H right here?
Yeah.
It? How about as a fresher memory of quantum mechanics?
그래서 그 H가 0으로 가면은 스핀 같은
Okay, maybe then you're right. If that's the answer. Really?
And rotations, basically.
Right, because this can describe just SO3 spatial rotation, and we still have to satisfy this algebra, right? Completely classical.
고전적으로 스핀이라는 퀀티티를 발견할 수가 없잖아요.
But this is also describe just classical rotation by 3 Euler angle, and they have to satisfy this relation, right? Anyway, so let's keep it. You two are responsible for giving us the ultimate correct answer by now. So let's move on, because at least I want to say something about the field. I haven't even started that, so let's do it. I knew if I say something about operator, it triggers someone. It did. Don't worry too much about it for now. So now let's actually talk about classical field. So now we want to consider a system of a field. So how we think about the classical field? Okay. So our previous discussion we had a generalized coordinate, right? Now we want to consider again generalized coordinate and t. So far notation change. But then we have extra labeling. So we have extra spatial vector labeling. So in this picture, you want to view, now I haven't promoted this to field yet, but there's a species index, like there's electron, muon, Higgs, whatever, right? But also, at each time, you want to consider the Euler freedom span over entire free space. And we're gonna now write this as basically species index and space and time. Okay? And we had a conjugate momenta. So we will introduce kind of notion. So we will have this object. Again, it has a many multiple infinite number of degree of freedom corresponding to both of this much full space. Okay? So we're gonna write this as this. Okay, so now, so previously we did this, right? So there's a dt integral and Lagrangian, and naive, generalization this to many degree of freedom picture will do this. However, we want to put a time and space on equal footing. Because that's when we can have a manifest notion of a Poincare invariance and so on. So we want to treat the time and space simultaneously. So for instance, this Lagrangian could have sum over some species index, sum over this spatial degree of freedom index. We could have, let me for now turn back to this notation just to illustrate the point. And then you can have many terms, right? So instead we want to pull out, this is sum with sum over entire space. So we want to pull out that together to write it as a sum over full space and time. Okay? And then we are going to call after pulling this out, the rest to be our Lagrangian density. So here, Lagrangian and Lagrangian density are related by I'm summing over space, and then I have a Lagrangian density. Okay, because this is L over V, so that's density. Now, what will be the form of then this Lagrangian density? Let's ask that question. So, in principle, this can be made up of, let's not consider single field for now, X. So I'm already combining space and time. So simple notation. And then this, you can go this. Okay? But just to simplify and then make the discussion as concrete as possible, let me just use these two ingredients. You will see more and more why that's okay thing to do for now, but eventually the theory can be constructed including those terms. Okay, which we will eventually start discussing in the language of interactions. Okay, but for now, let us take phi and derivative phi as two ingredients. Now, action is good to be seen with a single integral over space and time. Now, this is a manifestation of a locality. Why? Then this Lagrangian is made of a stuff, but eventually it's just a function on X. And everything happens simultaneously with a single point, right? A point. If you see, like, oh, I have my friend, I really like this guy, and he claimed that he has a beautiful theory, and he handed you to action, which is a D for X, D for Y. Stop talking to that person, okay? So that's deadly non-local crap, a lot of bad thing happens, and so on. So the lesson, not about your friend did. The lesson you want to remember is that the symbolically, mathematically, the fact that you have a single integral over space and time is now deeply connected to the fact that you have a local difference. Okay? Anyway, so let's move on. I want to construct a Lagrangian. So, what will be the possible Lagrangian, Lagrangian density? Okay, let's write down candidate. So, first some, index A, so some coefficient parameter A. What will be the Lorentz invariant object we can write down? Well, first I can write down this. Right? And then I can also write down this. For scalar field, in principle, you can also write down this, but I want to keep everything up to only quadratic order for now, as you will see why. So I'm not going to worry about this for a second. There's many things we can discuss. It's called the set pole. You can always, anyway, so for now, don't worry too much about this for a second, okay? Now, and then let's just look at this. Now, you can say physically, what does this A and B mean, right? So what I have done is that I'm going to use a single field. I'm going to use a phi and first derivative, and then I'm going to write down a Lagrangian, which is a Lorentz invariant up to quadratic in fields. That's what I have done. Okay? So now let's derive equations of motion. What do I get? So equations of motion, well, I haven't done the exercise, but if you do the same thing, well, let's just do it. I had to demand this again at the level of not field. Now, once you get that derivative, not Lagrangian density, with respect to field, and then you get plus surface term. I will let's do it exactly. Oh, I forgot one thing. Wait, cool. Okay. So you can literally follow the exact identical step as I have done for classical mechanics system. Okay, and you should get this if you follow exactly. Okay, so you will do it. So this is related to once again boundary condition. But suppose I say that phi goes to 0 as x goes to infinity. Okay, so on the boundary of space and time, let me impose Dirichlet boundary condition to kill this part. That means that under the arbitrary variation, I should get this to be 0. So that's my equations of motion. This is Euler-Lagrange equations of motion for classical field. So now, if we actually do equations of motion for that theory that I'm about to construct, let's actually see. What do I get? So first, I get 2a phi, so that's this gives me. And then the second term, minus, and if you have a 2 derivative, you have again 2b. I think you get this. Oh, minus, right? So that's the equations of motion. Now, recall that we are constructing a formalism that automates what we wanted to get as an output. And one of the output that we wanted to get, that if we want to have a field description corresponding to relativistic particle with mass n, I have to get this equation, right? This is completely general, regardless of the concept of the theory. All right, so if I look at that, then let's do a little bit of massage. First of all, I scale a and b to just 1 over a, 1 over b, to just get rid of these 2's. So that's probably what I want to do, right? Second, I want to just have a clean box A. So how would I achieve that? Let's rescale my field phi to absorb a b. So let me just rescale by this much. Okay? This type of operation that rescales your corner field, we will spend a time, it's called bad name. It's bad name, but it is sort of established. Wave function renormalization. So this is the dumbest example of wave function renormalization. If I do this to rescaling, your action will appear as this. So, how? Tell me. A over b phi squared plus del phi squared. So I'm simplifying my expression like that. Okay? So if I have done that as scaling, then if I derive equations of motion, I get, according to this, box phi minus a over b phi equal to 0. That's the equation we get, right? So if you started out your theory with this, that's what you get. So you learn the physical meaning of this. So minus a over b physically means the mass squared. So I might as well write it down. That means that I have squared minus m squared. Oh, I forgot half. Right? And a half here. And then half. Okay? Because I did rescaling first. So this is a simple theory to hopefully explain why Lagrangian take this form. Okay? So I wanted to have a scalar field theory, Lorentz invariant, local, and I can write down this and I exactly know why I had an m squared right there with the 2 derivative term here. Quadratic in action, because that gives me linear equations of motion, which is precisely that of Klein-Gordon equation. Okay, so far I just constructed the classical field theory action. Next time we will actually study the quantization, canonical quantization as well. Right, so that's all for today.